In this video, I'm going to introduce you to line integrals, and I will give you an example of one. So let's say you've got a surface given by this thing here. Just imagine as this, and your particle starts here and then it travels along this path. So as time ticks away, 1 second later, the particle would have moved from here to here. Another second later, the particle would have moved to here, and then another second later, it would have traveled from here to here. So here you can see that the particle is traveling really fast because it's a bigger distance, and then another second later it will end right here, so the particle will be here. So the particle is moving along this path. So the line integral of f over c, now this c is really this path here, so this c is talking about this path. So the line integral is really the integral of the function along a particular path. So let's visualize this from a Riemann's perspective. So from a Riemann's perspective, you've got your delta s. So delta s is really the distance along that particular path. So let's just look at time equals 2 and time equals 3. This delta s is really the distance along that particular path. So really we've got to use Pythagoras. We've got to use Pythagoras to work out that length, that diagonal length. So the idea behind the line integral is this: you move a distance along your particular path, which is this distance here, and then you jump to the surface. So from here you jump to the surface. So you move straight up here, and then you work out this area, because a length along a particular path, that's this length here, and then you times another length, that's the height to the surface, to the surface, to the surface. So that will then give you an area, and then another increment of time. So let's look at time, another increment of time. So it would be straight across, and then so that's this delta s, and then jump straight to the surface. So jump straight to the surface, jump straight to the surface. So so straight line here, and then you would work out this area here, because a length, which is along that's a length, and then you times the height. So this is the height here, and then when you get a length times a length, you're going to get an area. So you sum up this area, and then later on you take the limit as n tends to infinity, meaning you cut up into millions and billions of pieces. So eventually it becomes an integral. So the integral is given by this. Now from our section on parametric equations, the arc length is given by this. So we've seen this before. It's the idea behind this is if you've got a particle traveling in this manner from here to here, you would use Pythagoras to approximate the length along the path. So Pythagoras. Well, we've done this, and I'm expecting you to know this. You have to use the mean value theorem plus Pythagoras to come up with this, and we've done this before. So you might have to track back and look this up. Well, we've seen this before, so I'm expecting you to know this. Well, if you times both sides by dt, it will then give you this. This whole thing times dt. So now we can put this into the ds. So what that means is our particle up here, our particle is driven by this thing called time. So we're going to reference everything in terms of time. So by using our parametric equations technique, we can drive a particle along our intended path just by using one variable, time. So we can drive the particle along here, and the distance, which is ds, the distance along our path is given by this. So as you vary time, and then you multiply this by this magical thing here, it will then give you the distance along a particular path. We've seen this before, so I'm expecting you to be able to accept this. So times both sides by dt, and then we can, so ds equals this whole thing here. We can put this into the ds. So that will then give us this. That will then give us this. And remember, as the particle moves from here, hang on, as the particle moves from here to here, in our particular example it took 4 seconds. So what that means is, along here, remember, we've got to work all in terms of time. We've got to work all in terms of time. So in our example, it would be from 0 to 4, because it takes 4 seconds, and we've got to work everything in terms of time. But then this is xy, so we need to know a particular. We need to know the precise location of our particle in terms of time. So as we're driving, as we're driving the particle along here, we always need to know the x and y location of our particle for a given time. So we need to come up with a way to describe the x and y location in terms of time. I will give you an example. You will see, it's easier to understand when you see an example. So basically you need some sort of description on the x location and the y location in terms of time. And then once you know the x and y location, you will put that x location into here and put the y location in here, and then you will then be able to jump to the surface. And again, it will make sense when I give you an example. And this thing here is really your speed, is the magnitude of the velocity. And then you've got to integrate everything in terms of time. And again, it will make sense when you see an example. So let's give you an example. I will continue in the next video.